So maybe we'll take a step back on heat transfer and go very basics, maybe second year or third year courses, even going back to 9th or 10th of high school, right? So heat is a form of energy that we all know. We'll talk about mode of heat transfer. Actually, we already talked about those modes, but we'll look into a little detail. Then we look at the first law and second law, right? We saw temperature enthalpy diagram many times in the last 2 days, but today we will see why exactly we need temperature enthalpy diagram. Now, what's the importance? We'll do some heat integration, taking some examples like we've been doing for last 2-3 days, picking some example, doing our calculations and trying to understand the theory. Briefly, we'll look at some heat transfer equipments. Nowadays, there is a lot of pressure on energy recovery. So till now, in last 2 days, we talked about, if you remember, flue gas. We cool it up to 150, 160. We'll see today why only 150. Can we go a little bit deeper? Because actually 150 to 30 degrees, that's actually the energy lost to atmosphere. Can we still recover it? And at those low grade heat, if you can recover and generate electricity, so I'll explain a little bit more the Rankine cycle for power generation. So familiar first law, the total energy change of a system or of within the boundary limit is the work supply, heat supply, and EM is associated with the transporter. So if we exclude this, total change in energy will be either work supplied or heat supplied. That's the first law. It just talks about balance, like Dr. Kanti showed yesterday. Input minus output plus generation minus accumulation is plus generation minus consumption is accumulation, right? So that's only the balance. That's the first law. Right? Yesterday we were talking at some point that heat always flows from high temperature to low temperature. So flow is always from, let's say, high to low. The mass transfer, it's high concentration to low concentration. In even simpler language, water flows always from top to bottom. If you have to have flow of water from bottom, lower level to high level, what do you do? Pump. So exactly. So you have to put in some work. That's how you can defy the second law, that it goes from here to here. And in last few slides, we'll see how we can defy second law of heat transfer. So normally we can transfer heat only from high temperature to low, but there are systems where you can transfer heat from low temperature to high temperature. But then, as you yourself said, you need to supply energy for that. So we'll see that those heat pumps. Yeah. So first law only about balance, right? Second law, direction. So balance is fine, direction is fine, right? But we still don't know how fast, right? What equipment we need, how fast we can transfer heat. So that's the problem with the not problem, but second law doesn't cover how fast and how slow the heat flows. Right? So modes of heat transfer we already talked yesterday. You guys are, I'm pretty sure definition wise you are more familiar than me. You're still in the university. So that's the conduction, molecular interaction between the molecules within the metal, resulting in energy transfer. Convection, that's about the macroscopic fluid movement. And these are the three governing equations. Radiation we already talked about. The major difference between these two radiation is that's why electromagnetic. So hotter body, they emit these electromagnetic waves, they travel, and as these three are the governing equations. Let me show you all that for you. So, what is this lambda? Does anybody remember? Sorry? Thermal coefficient is this one. Who's that conductivity? Conductivity. So thermal conductivity. So when it's conduction, that's conductivity, and thermal coefficient or heat.
Sir, one more thing. I think in the first equation, instead of that partial differential sign, we can use d by dt because
D by dt, yes.
it's a one direction.
Yes.
It looks like one direction.
So actually equations are from
that's it.
book to book differ, but you are right. You can use dt by dx. So yes, thermal conductivity and heat transfer coefficient, thermal coefficient. That's this one. We already talked about this inside heat transfer coefficient, outside heat transfer coefficient, and combination of inside, outside, and conductivity altogether becomes overall heat transfer coefficient. So what I'm trying to do is trying to connect what you learn from the books and how this knowledge is applied in the real world. How this small equation is responsible for, let's say, cost of millions of euros here and there. If you do not understand this equation properly, you are not able to optimize or design your equipment properly. You are talking about millions of euros here and there. So, trying to connect the academic world with the real world. So, as we said, heat is a form of energy. You need to supply always. We talk about this inertia in very simple language. So every state, everything is in a equilibrium state, and you need to supply energy. For example, industrially to make products from reactant, a lot of changing equilibrium is required. So basically, we supply two kind of energy. We already discussed thermal energy and electrical energy. Thermal is mainly to change the state, increase the temperature, change vapor or liquid state. Right? And electrical energy is mostly used for moving the components. So you need to increase the pressure, move reactants or products reactants from point A to the reactor, products from reactor to the battery limit. So let's repeat quickly the same combined cycle power generation we discussed last time. So we take fuel, burn the fuel at high pressure, and let the flue gas at high pressure turn the turbine. So that's the gas turbine part. Goes into a flue gas duct. I think it's for some reason it's not clear, or it's only me who. Everybody can see those connections.
No, it is
no.
It is partially visible.
Yeah, partially
visible.
So, anyway, so flue gas, you extract energy, not thermal energy, but kinetic energy in the gas turbine. So that's first cycle. And you go in a flue gas duct, and then you generate steam at different pressure. And with this, you turn your steam turbine. Right? And here you could see it's not one turbine, it's actually one turbine, but you extract as your steam starts to expand, you superheat again and put it to the next stage, and superheat again to the next stage. So it's about increasing the efficiency, but it's one turbine at different stages you inject steam so that you can extract a lot of energy from the flue gas. You remember yesterday we talked about we can do air preheating, steam generation and feed superheating, but then suddenly we split the air preheating into two steps, because we want to extract energy at an optimum temperature level. So that's the reason here. You superheat as high as possible, extract the energy, re-inject energy in the steam, put it back in the turbine. That's how you do a little bit more energy extraction. Right. And we also saw that finally, end of the day, we cannot have full condensation in the turbine. So finally you have to do condensation somewhere outside. Let's do some simple calculations. Imagine that we have flue gas coming out here at 600 degree, right? And flue gas here going out is at 150. Okay. Let's assume we have 100 kg per second of flow, right? And the Cp value of flue gas 1.13 or 1.15. That's the amount of mCpdt gives me amount of heat capacity of the flue gas. Right? So simply m CP of 1.15 and DT 600 minus 220. Now, let's say we have to generate steam, superheated steam at 465, right? So if you remember the steam table we saw yesterday, I will go and look the steam enthalpy at 465 and the pressure, whatever it is. I know the enthalpy. I look at the table and I know the enthalpy. I know that's the duty. So the total duty divided by enthalpy of steam, right, will give me steam flow rate at this. Now, if you look at first law and second law, so second law says that heat always flows from high temperature to low temperature. So on the hot end, on this end, let's say 600 degree, and superheated steam is at 465. Very good, 435. It's even more than what we discussed yesterday, that there must be an approach temperature 30, 40, 50. It's higher, but okay. But it's satisfying the second law, not going against. If you look at the cold end, let's say the flue gas coming out at 150, and the water what we used for the steam generation, right, that's 105 for 45. Fine. So all well, both delta T's are positive, so heat is flowing from high end to. But now let's have a look let's draw the same thing on TQ diagram, temperature enthalpy diagram. So that's my water at 105 degree. Right? So the upper curve is hot curve, the bottom curve is cold curve. So we are trying to draw how the temperature let's say decreases for flue gas with the DT, and how the temperature increases for water, then steam, and then superheated steam for the duty, right? So we start with the flue gas. So 600 flue gas, right? And that's the outlet temperature 150. Okay? And that's the amount of heat, enthalpy, what we said. Actually, it should not be enthalpy, it should be right? 50,000. This curve is clear. Then we do for the water and steam on the opposite countercurrent fashion. So we start with 105 degree water. With MCPDT CP of 4.2, we start to heat it up while taking energy from here, went up to this point. This is the saturation temperature of steam. We increase the heat content or enthalpy of steam, and temperature is not changing so much because latent heat of steam is very high. So for the same temperature, you put in so much energy. You come in here, this is the saturation pressure or temperature, and then you start superheating it up to 460. So when we did only end to end, this end and this end calculation, everything was looking perfect, right? But in reality, it's not perfect. In this region somewhere, you have a temperature cross, right? You cannot have somewhere 220 degree water and 205, 210 degree flue gas. So this is the reason we are against the second law. So in reality, that's not possible. Dr. Gandhi, want to add something? That's the pinch point
exactly.
which we try to find. So what we have to do, we cannot have a temperature cross. That means I have two options. Either I should move this up or I move this down, right? So let's have a look on both the options and what are the impacts for both the options, right? So what we said we are generating steam saturation pressure, a temperature of 285 in our base case, main case what we discussed. Let's assume if we change our philosophy a little bit, and this is given for now. Let's assume this flow rate is given, so this total heat delivered by flue gas is calculated or given. Superheat temperature is also given, so 465. And now we say instead of 285, we generate steam at pressure it's 35 bar, 38 bar, which corresponds to 40 degree. So once again, it's the same thing what we saw in the previous slides, previous case, 135, 45. Still 135, 45. But what we did with this, we avoided the temperature cross. Now if you draw this, you are at 240, not 285. So there is no temperature cross. And what you normally do is try to see where your pinch. So this is called pinch point. Where in your whole profile is the minimum temperature difference between hot and cold. Now if we say we change here the steam pressure, but imagine in your plant you have a consumer which need heat at 260 degree. So if there is a process requirement where you need 260 degree heat, you cannot have steam at 240 degree. Of course, we are looking at power plant where you are generating electricity, but let's assume you need steam at 240 but 285, right? So with 240, sorry, okay. So let's assume we absolutely need steam at 285, right? So what we can do, we say we go at 600, and the flue gas, now we go out at 195. Flow rate is same. Again calculate M, Cp 1.1, whatever, and dt. Since this is increased, this is reduced. MCP. What it means, if I want to have no temperature cross or certain pinch temperature, right, and 285 degrees saturated steam, I cannot extract all the temperature from it. I can only go up to 195. So that's the downside of this option. So now 135, 45 became 90. Good. Temperature difference is increased. While UTD will increase. You will have cheaper exchanger. That's good. We do not have any temperature crossing. All well, right? But as I said, downside is almost 10%
loss.
10% of heat is lost to atmosphere. Right? Only 90%. So earlier it was 50800 and now it's 4576. So that's the downside or disadvantage of this option. But having said that, we need steam at 285 and we also don't want to have temperature loss. What could be the next step? We can look if there are any other low grade heat consumers available. So one consumer we are talking about at the moment is only steam. If there are any other consumers. So combustion, we already discussed a lot. Fuel, natural gas or coal, whatever, air, combustion. So that's the flue gas which is running the turbine in the first cycle. We already saw. Now energy content, this we already saw that energy content flue gas can be increased. In the hydrogen manufacturing session we saw we preheat the air from 30 degree to 450 degree almost. So ambient air is typically 25 depending on location. In reality, any kind of industrial combustion is always with hot air. You never supply cold air for combustion. You always have waste heat available, so you use it and preheat it. Up to 500 degree, it's a little bit on the higher side, but heating air up to 700 degrees also done. Not so often, but yes, it's done. So can we recover this 10% of lost energy in air? Yes, because air is somewhere here, starts here somewhere, 20 degree, 25 degree, right? And we can slowly use this. So you could see here this last energy in the flue gas, it's at temperature level 195 to 140. So we can use this energy. Okay, now we say we go even further. We say 285 and say if steam is required at 330, right? We saw going from 240 to 285 and satisfying the second law, we ended up 10% waste energy, energy loss, right? Not recovered. So you could imagine if going from 285 to 230, it will be even more. More energy will be left unrecovered. So first we saw how we can move this curve a little bit down, right? Now we'll see how we can move the hot curve a little bit up. And yesterday, Dr. Shena was mentioning that we do always combustion with air because it's cheap, easily available. Just put a blower and you have your combustion air. But imagine we have from here to here somewhere around 50,000 it was, 50,000 kilowatt of energy, thermal energy, and the flow rate is 100 kg per second. Imagine if we do not supply air, we supply only oxygen, because only oxygen in the air is used. That's what we want for combustion, right? So imagine if we replace air with oxygen, right? Your flow rate of flue gas will be reduced by factor 4, based on 79 to 21. So with every 10 kg of air, it's only 2 kg of, roughly 2 kg of oxygen. So whatever air is coming, if you remove 80% of it, it becomes factor 4. Flue gas will be factor 4 less. But fuel burnt is same. That means energy release is same. So if you look at Q is mCpdt, and M becomes suddenly 4 times less, Q remains the same, delta T will be much higher. That means if I start using oxygen instead of air, this temperature will go somewhere here. But it will end up here, right? But this curve will, let's say, move a little bit up. So instead of oxygen, instead of air, if I use oxygen, I move this temperature up. Now I'm somewhere here. Right? So that's another way to optimize it. So you still don't have any temperature cross, and we have 330 degree saturated steam. So far we looked at the temperature enthalpy, first law, second law, and how this is applied in really equipment design, and how it impacts the cost of your equipment. So we said, we just continue with our example. So the flue gas is going at 150, right? Now we are looking only on this air preheater, not the steam side, but only this part. So what's the duty here? What's the temperature here? So hot side, flue gas 100 kg per second. If you remember our basis, temperature was 214. Up to 214, from 600 to 214 was to the steam, and from there it's to the air. Air comes in at 25. We do the calculation. If you remember, for 100 kg of flue gas, it was somewhere around 10-12 kg of fuel and remaining air. So that's the combustion air, 90 kg per second. And if we once again do mCpdt, we know the duty, right? With this duty, once again mCpdt, I know the delta T, and that's the temperature of air, right? Nothing new. Again, applying this hot and cold and thing, 131, 125 is good. 128 LMTD. We'll see LMTD a bit later. Now, the question would be, why 150? You can go a bit deeper also. If I go instead of 150, 100, I can preheat the air more. And hotter the air, we already saw yesterday, less will be the fuel consumption. And that's less money you pay on your operating costs. So let's try it out. We go from this case to this case. I go now, temperature out is 100 degree, and I am now a little bit more preheating more the air. LMTD, the temperature difference is, you see, 240 minus this is 83, here 169 minus 87, 81, 100 minus 25, 75. So temperature difference is slightly decreased, LMTD decreased, that's my duty decreased, because now we are recovering more energy from the reverse. Preheating the air more, it means we are recovering more and thereby reducing the fuel consumption, right? So see, flue gas to stack reduced by 50 degree, right? Air combustion air increased slightly 4%. So difference here is 400 kilowatt, 5085, 5485. And it's almost 1% of your total duty. So 1% total duty means 1% saving in fuel, which sounds small, but in real world it's huge. It's a huge difference, 1%. But if we extend now our thermodynamics to engineering, as we said, it doesn't end at only the LMTD and the duty. But let's assume the overall heat transfer coefficient for those two cases are same. The area required will be, I can simply calculate based on Q is UA LMTD. Right? So Q we know, U we assumed, LMTD we calculated. So if we just take these three and do the maths, you end up here. For this case, you end up here. So the same capex opex trade-off optimization we have been talking for last 2 days. You save on fuel, but you have to pay more on the heat transfer area. And heat transfer area times thickness of your tube or plate or whatever is your material or metal, and metal is your cost. So let's extend this to even further, go further deep, 150, 100 case we saw, and we go to the next level 50. Look at the area, it increased by, I don't know, 70%, 60%, 1300, 100, 70%. But look at the area increase from this point to this point. So the heat recovery was 10% higher or 8% higher, or 10% let's say, for roughly 400, almost 5,000, maybe 8%. Here another 8%, but look at the area. It's almost 250%. What we see with deeper energy recovery, you are reaping the benefits, you are saving fuel, but somewhere else you are paying a lot. There's always that's what I've been saying constantly, always a trade-off between, you have to understand the systems. You see, if you just look at a smaller picture and think about it, okay, I save fuel, then, but if you consider cost of your heat exchanger, your optimum lies somewhere else. Maybe better to stop somewhere here or here. We'll see those. Now, overall heat transfer coefficient, we looked at this alpha or H, different people call it different way, but individual heat transfer coefficient on one side, hot side, cold side, and together with the thermal conductivity of your metal separating hot side, cold side, it becomes your overall heat transfer coefficient. But here I'm showing just one familiar equation for defining this convective heat transfer or calculating this individual heat transfer coefficient, basically for the liquid states. Yeah, as you said, combination of hot and cold, and also the conductivity. And H is based on two parameters. So one is related to your design and flow regimes, right? Another one is defined by your properties, right? So transport properties like specific heat, K, mu, etc. etc. If I remember correctly, Renault number D is dV rho by mu. So it's basically D is representing the design of the equipment, what diameter you are selecting. Velocity once again representing your conditions, flow and diameter what you are selecting. So this one is more dedicated to
This equation looks like very beautiful because it relates heat transfer with fluid mechanics
yes. Yeah.
because of RE.
Yes, yes, very good comment. And Prandtl number CP
upon K.
CP mu by K. So all transport properties, CP mu K, all are transport properties. So that's more dedicated to fluid properties or system you are handling. So coming back to this area, we just plot these three cases. I smoothly plotted it. That was 5080, 1333. I go from 5080 it was, I remember, 5485. We were somewhere on 1300. But looks another 10% addition. So we were 5800 or something. We were somewhere around 6300. So look how the area exponentially increased. So it's a typical curve to represent the effect of increasing capex, decreasing opex, or increasing opex, decreasing capex. If you put our example on this plot, we started somewhere here. Our operating cost for the fuel was somewhere here. We moved a little bit here, and we reduced the fuel consumption, so operating costs reduced, but our capex increased, right? But the third point was we moved from here to here suddenly. Our capex or the area increased like this, right? Our opex reduced somewhere here. But combination of opex and capex, that's our total cost. And look at the total cost. So in the starting we were here, first point. Second point we were somewhere here. But third point suddenly we once again increased it, right? So there is always an optimum between capex and opex. So that's the point we have to find for the minimum cost. So there is nothing like minimum opex or minimum capex. We will see in coming lectures or coming sessions how we combine these two. You cannot simply add these two things. There is a way to combine this, but you have to find always the optimum point for the minimum total cost. Now, you could imagine if you are working on such exercises or such cases, you cannot do such detailed calculation every day. Right? So that's why you have design rules. You, based on experience, people know that, like we said, 20-degree approach temperature for a boiling system. For here, we are somewhere around 130, 125. So LMTD is 128. So people work with LMTDs. So we know if we have, we'll see once again in coming slides. But for such an application, LMTD of 50 would be optimal. So you could see LMTD goes down, area goes up, but your recovery is not so high. So for such application, where you have gas phase on both sides, and both the gases are not under pressure, atmospheric pressure, gas side, or both fluids are in vapor state, gaseous state. So somewhere around 50. If you have gas on one side and if you are generating steam on the other side, so steam has very high return potential, boiling service, right? So then probably 20, 25 LMTD is okay. If you have water on both sides, maybe 10, 15 or even 10 is okay. So there is an optimum, because you cannot do all the time plotting this curve, how it's going up, what's my total cost, not do every time. So you work with these design rules. You remember that, okay, for such I take 50, for water I take 10, There are some special design of heat exchangers where even temperature difference LMTD of 3 is possible. Yeah, as I said, design rules to avoid time-consuming tailored optimization. I guess everybody is familiar with this thought. So we talked about yesterday LMTDs or counter current, hot side, cold side, parallel.
So in parallel flow, that right hand side temperature, that is
Which one?
Right hand side.
This one?
Right hand side temperature. Both temperatures will not cross each other.
No, they are not crossing.
If it
So
is
that's
cross,
the hot, that's the cold.
This outlet temperature.
Outlet temperature. That's inlet, that's outlet. Hot side, cold side. They are not crossing, right? Hot side, cold side.
Because curves start from like this travel like this, and from upper side it travels like this. So they will not supposed to cross each other, right?
No, and they are not crossing. The same example with co-current, same example with counter current. So they are also not crossing anywhere. But you could see that's my starting point, right? It's my starting point, but I can have very high cold outlet temperature.
Cold outlet temperature.
Now the question may arise, why we know counter current is the best mode for
Heat transfer.
best heat transfer, right? But then the question may arise, why do we have counter current? There are times where we use counter current also. Can somebody think about what could be a advantage for no? Okay, so let's assume we have same case, gas and air, flue gas, air, flue gas, air. So log mean temperature difference we talked about, end to end how we do the overall approximation. But let's do from here to here the point temperature difference. LMTD is nothing but representing point temperature difference over the whole length. So at this point, at the inlet, metal surface would be, if I say both are gases, right? So similar heat transfer coefficient. That means the temperature profile would be, temperature drop would be somewhere around 45% here on the hot side, 45% on the cold side, and remaining 8-10% on the metal side. So my metal temperature would be somewhere here. As I go further, my metal temperature remains similar, right? Now look at this one. At this point, my hot side inlet is this, cold side outlet is this, my metal surface is somewhere here, right? So my metal temperature is much higher in this case. So if we are talking about services where you are, so with this one, let's assume this one and this one, LMTD is much higher, LMTD is much lower. LMTD is higher, but metal temperature is higher. And you might end up in a scenario where due to high metal temperature, you have to change the material of construction. So this material of construction costs 3 times. You are saving 50% on area, but you are paying 3 times more per kg cost of this metal.
To just replace the material of construction.
So then I agree with more area, but with this I can use a cheaper material, right? So my overall cost of exchanger is much lower. So those are the scenarios where you actually sometimes use co-current as well. There are many other cases. Sometimes you have temperature sensitive case. Very good. That's what I wanted to just explain now. So imagine you have a hot side flue gas, but on cold side we don't have air. We have natural gas, and natural gas has a tendency to crack at certain temperature, 650, 670. So if you have natural gas in your pipes, you don't want to have
heat sensitive material.
Heat sensitive material. So there you want to have cold Another example we saw from yesterday, the boiler, where we have this metal dusting corrosion, and we didn't want to have temperature window of 400, 700. And we said we go from 800 to 350 directly, thereby having water on the other side. So there also we use co-current. Right. If we use counter current in that scenario, what can happen? You have 850 reformed gas or product gas with very high CO, and you want to have cold side seeing this temperature. You put the hot side on this side, means counter current, your metal temperature will be higher. So although people think that LMTD is higher, then we just take this one, but there are some distinctive advantage of co-current as well. Sorry, I forget to change the heading sometimes, but so we saw here that's pure counter current, right? You enter here, you exit here, you enter here, you exit here, right? So it's purely counter current. At every point, the hot side and cold side fluids are flowing in opposite direction. But in reality, so we said this is actually your HD by K. HD by K. So H is your heat transfer coefficient. And at any cost, I want to increase this Nusselt number. Right? So there are several ways. What you can do, you can increase velocity. Properties you cannot change much because properties are inherent properties of fluid. They depend on temperature.
It is associated with fluid.
It's fluid, so you don't have much influence on this one. So RE is the number what you have at your hand as a normal, based on your design, what diameter of tube I take, that will define your Reynolds number, and that's how you can actually influence your Nusselt. So RE is nothing but representation of the turbulence in your system, right? And turbulence is nothing but representation of how fast these molecules are moving here and there. And if they are moving fast, they will also be able to give the energy to the next one faster. So for heat transfer also, we want to have very high very high turbulence. Turbulence you create by higher velocity because Reynolds number is dV by mu. What? dV by dV rho by mu. dV rho by mu. So velocity you increase by doing something in your design, and you have a piece of equipment. Now you think about what can I do. So let's say you have an exchanger, you have hot fluid going in, cold fluid coming in, coming out. So in this region, it's purely counter current. You can see purely opposite direction counter current. But in reality, if you have fluid coming in here, right, you do not have very high Reynolds number on the shell side. So what you can do, you put some baffles. And then fluid starts to flow, the cold fluid starts to flow like this, like this, like this, like this, like this. So what is the impact of going from here to here? From here to here, the pressure drop was low. But suddenly, your flow length was only this, and delta P is 4FLV square over 2 GCD. 4FL, your length is this much. Right? But what we did here, we increased the length, flow length. The flow area was cross-sectional area here minus the tube area, but here the cross-sectional area is only this, so in this direction. When you increase the velocity, right? So delta P going from here to here, your flow length is increased, your area is reduced, delta P is much higher. So delta P is higher means pumping cost is more. So that's your OPEX increase. But while doing this, you drastically increase your Reynolds number because you enhance turbulence. If your Reynolds number is higher, maybe you can reduce the size of the cylinder because your H is higher. H is higher, U is higher. U is higher, your area is higher. So once again, you see how this small equation is dictating your capex OPEX optimization. So pumping cost versus exchange area. In the other example, we saw fuel cost versus exchanger area. So we saw here that's co-current, that's counter current. Right? And you see any equipment, heat transfer equipment in world or in industry, it will never have pure counter current fashion. Right? Apart from double pipe exchangers, we'll see the computer which are rarely used nowadays. So either, so if you see here, in this region you have cross current, because this is cross now. Port fluid this way, hot fluid this way, cold fluid this way. In this way, it's also cross, but overall is cross counter. Right? So it's not pure counter current. So we cannot calculate LMTD. So one way would be you calculate LMTD for this reason, for this reason, for this reason, for this reason, for this reason. But that would be very time consuming. So that's why you have LMTD correction factor. You don't use LMTD, but you use LMTD correction factor. So with this correction factor, you correct your LMTD.
Sir, last slide, can you please repeat one more time?
Sure.
Because,
Which one?
Bottom one.
This
Multiple LMTD.
So ideally what you will do your QA LMTD equation here, here, calculate your LMTD for only this reason, temperature here, temperature here, temperature here, temperature here. That's even cross current. So what I want to say, this is your pure co-current, counter current.
Sure.
But in real exchanger, you have in some reason co-current, some reason counter current, some reason cross flow.
Okay.
So it's a kind of mixed
flow.
Mixed temperature difference.
Okay.
And ideally, if you want to do real calculation, detailed calculation, you split it into different zones and do your calculation based on LMTD co-current, LMTD counter current, LMTD this. But in reality, what you do, you calculate LMTD based on counter current and correct it, update it with a factor called FT,
Correction factor.
which is always lower than 1. So one means it's pure counter current, and lower than 1 means how far you are going away from counter current flow fashion. How your design is. So let's say if I have 0.9, that means I'm far away from pure flow current fashion. So as we were saying, I was telling different U values. So if you have water to water, very high U value. Generally we use 1200 to 1500, water to brine 580 to 1150, because brine tends to scale. So, organic liquids a bit slower, condensing service you could see very high, 1500, 1800 is normal. Water to gasoline 340, 570, gas oil even lower, because as you with the petroleum cuts, as you go heavy, gasoline is slightly lighter than gasoline. If you remember something, petroleum product which is lighter than gasoline. What we use normally or use normally at homes. What? LPG. So the first one is methane. Hardly you get from heavy crude oils, but LPG, gasoline, petrol, naphtha, diesel, kerosene, fuel oil, heavy fuel oil, and then finally bitumen, asphalt, all those carbon black, wax. So as you go heavier, their fouling tendency increases. You cannot have very high U value, because U value is also directly showing what velocity you are at. And then for safety, somebody was saying about static charge. You have static charge from your shoes, this and that. But sometimes for gas oil or heavy gas oil, your velocity in pipes, tubes is also limited by this reason. Because if you have very high velocity, you can also have static energy or static charge, and then suddenly it can crash back. So water to air, so you could see condensing very high, liquid still high, fouling service would go low, boiling water is again on the higher side. As we start to add the gases, air, flue gas, all those things go for the lower. And our example is unfortunately not represented here, but flue gas here service at atmospheric pressure somewhere around 10 to 20. Compare this with this. Imagine you have a condensing steam and something else, some other liquid on the other side. We are talking about 2000, and if you have flue gas air, we are talking about 20 to 25 degrees Celsius. What it means, for the same duty, you can have an exchanger like this. You have condensing steam also, and for same duty, you can have an exchanger half of this room. Heat exchanger which fits in half of this room. Duty is same. That's the impact of U, and that's why it's absolutely important to design it properly and calculate your H value or U value correctly. So once again, I already did this, but relating our example, how we go from low, high LMTD to lower, how our operating costs reduce, our capex increase, but overall cost is somewhere here. So with this example, we are somewhere here. With this example, we are somewhere here. But we want to be in this region somewhere. This one is the optimal solution. To maybe 100 grams per normative flue gas. So you need to clean your exchanger regularly, not like others, some shell and tube exchanger which you need to clean every 6 months, every 8 months, every 1 year. But this, with the dirty service, you need to clean it continuously. There are online cleaning mechanisms. I was mentioning with some special design, you can go even as low as 3 degrees centigrade, LMTD or temperature difference. And that's a typical example, plate and frame heat exchanger. You have several plates stick together, or just screwed together, and hot and cold fluids are flowing in the alternate spaces between these plates. And since space is very low, the local velocities are very high, that's why the transportation is very high. And major advantage of this design is, compared to shell and tube, you can put a lot of heat transfer in a very small compact exchanger. So the space requirement, flow requirement is much lower. But disadvantage on the other side, you cannot use it with the fouling service. Regular cleaning, it's not a good idea with such exchangers. And as we said, local velocities are very high turbulence because of very small space between the plates, especially compared to ocean. But there's a major advantage, the U value could be 3 times higher than the shell and tube. Then we saw we have huge exchangers here, a lot of area required here, and that's one way reducing the area or increasing the transfer coefficient. You have extended surfaces, so you just put in metal, and the cold side or the hot side can transfer heat via convection, and you enhance it via convection. This metal is also heated up with the bare tube, and there are several designs of. Once again, optimization is between how much U value you increase and reduce your exchanger area and cost, and how much extended surface or metal you are paying. So we saw that in the starting we discussed that we can recover heat up to 150 degrees. We had a look what are the downsides of going lower in conventional way. If we use a heat exchanger, how suddenly the heat exchange area shooted up or decreased, right? So, and I briefly said there are ways you can defy the second law, and transfer heat from low temperature, high temperature. But to do this, you have to put in some energy, some form of energy. Right? And that's what we will see here now on two slides, last two slides. So first one is heat pump. So let's say I have waste heat in flue gas from 100 to 50 degree, because we already said our optimum temperature is 100. We'll stop there with the exchanger. But we know there's still some energy left between 100 to 50 degree. Can we do something? But we do not have any user. So what we can do? We can have an organic fluid. It's in a closed cycle here. What you do, you heat up this organic fluid and cool down your flue gas from 100 to 50 degree, right? And this organic fluid then goes to the compressor. You compress it. While compressing, your temperature is increased. So it was in liquid form here. You vaporize it, you compress it to high temperature, goes in somewhere here, it condenses at high temperature. So requirement of this organic fluid is it has to vaporize at low temperature and condense at high temperature. Right. Once it's condensed, you simply cool it down again, flash it from high pressure to low pressure. It's again at low temperature, becomes liquid. That's how it keeps circulating here. So form of energy what we are putting in here is running this compressor. By this what we are doing, so you see 100 to 50, that means my organic fluid must be at vaporizing at 40 with a 10 degree temperature. 50, 20. And if I want to have heat at 150, it must be condensing at 160. Once again 10 degree between hot and cold. So my requirement for hot organic fluid is it must vaporize at 40, condense at 160. And the energy what we put in is this energy to run the compressor. With this what we did, low grade heat we transferred it to high grade process. And that's called heat pump.
Heat pump.
You pump from low to high. The same way when we say you pump water from low level to high, low pressure to high. So that's one way. Another way is ordinary Rankine cycle. It's very common nowadays, especially in cement industry. So once again, you have flue gas at 100 degrees centigrade. You know what to do. People normally do is exit in the atmosphere. But what you can do, once again, use another organic fluid, right? And use this flue gas at 100 degree and exiting at 50 degree to vaporize at high pressure this organic fluid. High pressure organic fluid will be turning the turbine, it will be expanded while generating electricity, goes to low pressure, it's condensed. Once condensed, so you know the pumping liquid from low pressure to high pressure is much cheaper than compressing gas from low pressure to high pressure. So simply compress it once again to high pressure, once again vaporize it. So that's the closed circuit for this organic fluid. And this pressure drop here or expansion here will give you electrical energy. So that's another way of recovering this last or squeezing the last part of the energy left in the flue gas. Till 5 years ago, nobody was doing it because the cost of such setup was very high. Which once again, capex OPEX, what we have been talking for the last 2-3 days. But since there's a lot of pressure on energy recovery, so we talked about this going from energy CO2 intensive energy source to low carbon, and one of the slides I also showed to increase efficiency. That's also a way, maybe a smaller way, but a way to reduce CO2 emissions. And that's one example. Earlier people were exiting this to flue gas to atmosphere, but nowadays they extract energy even from the last end, so that you have less energy consumption, thereby less CO2 emissions. Yeah, with this we conclude the first session. If there are any questions,
Be interactive. Anything you could not understand or any query based on the presentation.
So theoretically, can we in that parallel flow, parallel flow heat exchanger, can we cross that outlet flow?
which one?
The parallel flow?
Here?
Huh?
So normally you cannot.
Theoretically.
Theoretically yes, but what you can do, you can have two passes, right? So you can have two pass on the pole side, so it goes like this and here, right? And then you can have a cross. So first pass it will be co-current, right? And in the second pass it will be counter current. So if I draw two pass, that's the side where its cold fluid is entering. On this side it's returning, it going here and exiting somewhere here, right? So you could see here you can have a cross. So that's the counter current. So one pass is co-current, another one is, that's the pass way.
Means we have to increase the number of passes.
Yes, number of passes. So you can increase here two pass, you can increase here also two pass. Like this.
Means one shell pass, two tube passes.
So two tube passes. Now we have one shell pass, one tube pass. It goes here and here. It's one shell pass, two tube pass. It goes here and here, two shell pass. You can have two shell pass as well.
Of course, sir.
Two shell passes. But it's okay. When you increase, it's a good question. So if you increase on tube side from one pass to two pass, how much the pressure drop will increase on tube side? You increase same cylinder, you split on the shell, the tube sheet, you just put a plate. Now you have not one pass, you have one pass and two pass. How your pressure drop will increase on tube pass? Think about, you have reduced your flow area by 2. And how flow area is related to pressure drop? Delta P is 4FL V square over PGCT. V square, V is nothing but
velocity
flow divided by area. If you reduce area by 2, effectively the pressure will increase. So yeah, once again, capex opex, what we always talk about. You increase one pass to two pass. You increase LMTD, you reduce area of index area, means you reduce your capex. But on the other side, you increase your pumping cost or your pressure on the side. So you have to find a balance.
It will lead to the less residential time.
Yes.
One more thing, just like a graph, that correction factor LMTD graph.
So this plot
R
is just an
and P,
example.
that R and P, it's the ratio of temperature, means T is capital T and small t, na?
Yeah, actually I just picked the plot.
Capital T is shell side temperature.
If I'm
Shell
not
side
wrong,
I think
capital T are the hot side, yeah,
No,
and small
no,
t
I
is
think
the.
shell
But I
side.
simply I just picked a plot just to give an idea that you need to have a
Small t represent tube side temperature, capital T represent shell side temperature. It looks like on the top right. That additional graph.
R must be the hot side because you see R values are more than most of the time more than 1. Otherwise, R is cold. You always have.
So if correction factor is 1, means it's purely counter.
Purely counter. That's correct. That's why we
And
have
less than 1, it is how far away from
Yes.
counter current.
small t used to be the representation for cold side.
Cold side. That's what I meant.
And capital
Hot
T,
side and cold side. Yeah. If it's other way, then we'll never have R more.
वो उसमें सर ट्यूब लग रहा है, वो जो ऐसा सर्कुलर लग रहा है ना, तो T2 इनलेट होगा और शायद ये T1 इनलेट होगा, T2 आउटलेट होगा उस सर्कुलर में, और ऊपर जो लग रहा है वो शेल साइड है, वो ऊपर में T कैपिटल T वाला.
शेल साइड हो चाहे ट्यूब साइड हो,
हॉट साइड.
नहीं ये
हॉट फ्लूइड जो है
हाँ, हाँ.
उसका टेम्परेचर अपने को कैपिटल टी से रिप्रेजेंट करना है और स्मॉल टी से कोल्ड साइड, चाहे पास मतलब आप ट्यूब से दो या शेल से दो.
What I wanted to show with this is there is a factor first of all, and you don't have to sit and calculate this factor based on आधा मेरा half of my exchanger is counter current, half of my exchanger is covered. There are plots available. You simply look what design I have for 2 pass, 4 pass, 2 shell pass, 2 pass. You go and pick this plot. You have this plot. You look at your.
So we need to calculate P value, R value, and we have to extend the lines.
Yes.
In the graph.
So you calculate.
We can calculate the correction
pick
factor.
your R curve, and then you have your. That's what. So these plots are available. You don't have to do the calculations. One step further, these plots are even, let's say, implemented in softwares. So normally you don't do hand calculations for randomly. Software is available. All these equations are already implemented. Flatting database is there. So you just have to specify composition of your gas or whatever. It will calculate everything. You just have to design it and keep changing number of passes, then more questions or we take a break?
बताओ, क्वेश्चन बताओ.
Pinch point.
Sorry?
Pinch point.
Pinch point. Why pinch point is a very good question. So we you know this equation, Q is U O U A LMTD, right? And LMTD is nothing but the average temperature difference between hot and cold side. So you can have arithmetic mean, you can have there are some other ways of calculating mean, and log mean is the best of approximation, as Gandhi said yesterday, right? So total area of heat exchanger is, you can calculate also, you divide total heat exchanger into different elements. So if I take this small element, my temperature difference is this. But if I have very small pinch, right, that means my temperature difference is very small, right? So you could imagine very small duty transfer, but very huge amount of area required for this place, right? So that's why you do not, you say I accept only minimum pinch of 10 degree. Means with 10 degree I know I have an optimum area requirement. If you are very low pinch, then you are putting a lot of area and this area is not doing much. So that's the concept of pinch. You need to find where your pinch is and you need to decide what pinch is acceptable. That explains. Anything else?
सर ये वाला बोला था मैं, ये वाला, ये जो है ये दिस कैपिटल टी रिप्रेजेंट ओनली शेल साइड, कैपिटल टी इनलेट आउटलेट,
Yes.
and that small t
is the tube
represent
side.
for tube
Yeah.
side. So the difference
As
between
Dr. Shende said, it can be shell or tube.
He is
but
also
what we
correct.
meant is
Correct.
the hot side.
That is the standard convention.
Exactly.
But yes, similar. plots.
Similar.
Yeah.
Yes, we have heard 2-4 shell and tube heat exchanger, 1-2 shell and tube heat exchanger. Is it possible to have 1-3 or 2-2? Can you do some thoughts on this front?
Two tube and two shell.
Yeah.
Two
left side high and change we can increase, but it will also increase. So decrease the area. It's the transfer.
Just geometry and possibility of operation we have to think upon.
If we increase those passes on tube side, it will increase the area. So floor area will increase.
Yes. Anybody? Who is working on heat transfer? I mean, the project related to heat transfer or something like that. No one is working on heat transfer or that kind of concept. Okay. On which area you are working?
Area first year.
Okay. Second year? Yes. Yes. You are doing
Modeling and simulation.
modeling and simulation. Okay. So, do you model condenser, heat exchanger?
Actually, I'm focusing on the interactions between molecules.
Molecular interactions.
Molecular interactions.
Okay. Is there any application of heat transfer
No, sir.
on molecular simulation of that kind? Whatever the concept you are dealing with, do you feel heat transfer comes across? Or not?
हीट ट्रांसफर तो नहीं आता, मतलब हीट का इफेक्ट पड़ता है इंटरेक्शन।
अच्छा, तो उसमें शेयर करो ना, कैसा इफेक्ट है?
सर मतलब कुछ मॉलिक्यूल्स ऐसे होते हैं कि समझो हीट मतलब हीट सेंसिटिव होता है, तो इफ हीट हमारी हाई तो इंटरेक्शन मतलब बहुत अच्छे से, इफ हीट नहीं हुई तो वो इंटरेक्ट नहीं होगा, मतलब हीट सेंसिटिव मॉलिक्यूल्स होते हैं।
Heat sensitive molecule means the moment temperature increases, or if they come across to some higher temperature, they will be decomposing.
Yes.
They will be breaking down, converting some other molecules,
Yes.
like that. So anyway, that effect is related with the intrinsic characteristics of the particular molecule. Okay, so there also you can play with these concepts and protect your molecule, right? You can play with some specific arrangements, right? I mean, you can do some specific arrangements so that the molecule will be protecting to the exposure. I mean, exposure will not be there because of that arrangement which you will be arranging, and the molecule will be protecting. If we want to protect and we do not want to waste or degrade the our stuff. So in that spirit also it is usable. So that kind of understanding and our appreciation should be. That is what the applicability of each and every concept you can draw with. Okay, because every talk or every literature may not be directly applicable, as it appears may not be directly applicable, but if you give some thoughts, if you appreciate the concept of that particular thing and your application, so some relations can be drawn. That is what my point was. So now we conclude that there is something which we can learn, which we can adapt and put into our applications. Your topic. Okay. First year have not started to work upon project.
No, sir.
Not yet. Okay. Your BTech also you can remember BTech project. So there also you can think upon, right? Because we do project just to get the insights of the particular aspects. Project means what? Some aspects we work upon, right? And we try to understand to the intrinsic level of that particular objective. So interpolate is also, okay. You can enrich your understanding and you can put into some advancements in your understanding. वो चीज जो है कर ठीक है. Yes, any other questions related to-
Sir, like we have the turbid fluid, so which side is good, like a shell side or?
Good question. So normally the scaling of the fouling fluid you put in tube sides because tube side it's much easier to replace. You simply sometimes put the jet of water the tube. So generally tube side is much easier to do.
Turbulency. He's asking about turbulence.
I thought turbidity you said.
Turbid.
Turbidity or turbulence?
Only turbid.
Turbidity, na? Dirty fluid, the fouling fluid where you have scale formation and those things. Yeah, those things we normally put in tube side because it's much easier. Imagine you are putting the fluid which is fouling, it's fouling tendency. You put it in the shell side and to clean the shell side. Yeah. So to clean the shell side, you have to open the whole exterior, right? And then spray the water jet on the outside of the tube because the scale formation will be on the outside of the tube. So it's very difficult. But on the tube side, you simply put high pressure water jets on one side without dismantling the exterior. So that's why it's better. Yeah. The scaling of fouling tendency fluids on the tube side.
Even the cost of the tubes used to be relatively very low,
Yes.
right, as compared to the shell, right? So if you need to replace because of the fouling and those problems, if you need to replace the particular element, I mean in this case tube, so replacing tubes will be always beneficial and economical, right? Because if something happens, you can drop back that tube or entire tubes and put the new tubes because those are very cheap. Right. So that is also another way. Right. Some corrosive nature of the fluid if it is, so that will be corroding. So rather than putting into shell side, put those in tube side. Right. So even at some moment of time you find that it is corroded, replace. So those kind of techniques we have to keep in mind. Yes, that if the flow is turbulent, suppose one flow and there is another flow, right? One flow is turbulent, then which side we should use that turbulent flow? Every other characteristics remains more or less same of the two of the fluids, right? Then which side we will be using for turbulent? Shell side. Are you agree? All?
We also use like baffles for
Baffles
the
to increase
create
the
turbulence within the shells.
Yeah, because you are giving some more area in shell, right? So that the further turbulency is unlike.
Yeah.
So that is one way to understand if you agree. If you put into tube sides, again they will have very little area to pass, and again turbulency and those kind of problems will be increased.
In this you will be provided a small system like this on paper, and then in a group of 3 or 4 you will sit down and think about some guide words at least and some parameters, talk about what can happen, what can go wrong, and if you see all the systems are there in place and come up with a communication. So for as we said, we identify the risk, we identify if the safety measures present are enough or not, right? But so far we have not identified just the strength of the safety measures. So we call it the safety integrity level, these measures, safety groups. And that is based on, so each risk can have a final consequence, right? And we try to reduce the risk up to acceptable level. So as we were saying, we can accept 2 fatalities in 1,000 years. So that's the number before the cell study you fix. You say, okay, that's my acceptable risk. And now I go to my design where the HAZOP recommendations are all already implemented. So all the safety measures are there. And now I have to see what exactly is the strength of or goodness of this safety, these safety measures required. So actually this is, let's say, in the conceptual stage we did the hazard identification. In HAZOP we did the HAZOP, also some hazard identification, some are problems. But in HAZOP we basically confirm that all the safety measures are there. If some are missed, we recommend something. And this is the last final step, at least in design, to come up with a safe process, safe plan. Right? So as we said, the HAZOP concludes with some recommendation to provide safeguards. Yeah, so safeguard present in place are enough to reduce the risk to acceptable limits. So let's do a small cell study on the same example. So we said we have all the safety measures as per the recommendation. TIC is also implemented, right? So you start with what exactly is the risk? Multiple fatalities due to fire caused because of flammable components, loss of component. This we already declared, already said. If all layer failed, ignition source is required. First of all, we can have loss of containment, but the final consequence of fatalities will happen only if we have combination of two. If fire occurs and if people are present, unfortunately, close to fire. Right? So we talked about the fire triangle yesterday. We need ignition source, right? So spilled flammable liquid might catch fire, might not. So sometimes everything failed. You have liquid gasoline or whatever in this tank came out, but still you could be fortunate enough to not catch fire. It's not at auto ignition temperature as long as it's not at auto ignition temperature. Ignition is also a probability, right? That means similarly for all so far we were saying if this fails, if that fails, if this layer fails, but all these layers have a probability of failure. They can fail maybe every day, but every day you don't need it. You normally have your operation at a normal condition. First of all, there is a probability of temperature increase or pressure increase. Then for this let's say occasion, you need this pressure loop to act, that it sense. So there is a pressure transmitter which is sensing the pressure in the vessel. So when pressure is increasing, then you need this pressure sensor to act. It must deliver when you read it. So first of all, there is a probability that pressure is increasing, and next, when you need it, this pressure sensor to work, there is a probability it will fail. Right. If this fails, the next one fails. So we'll see now how you add all these probabilities mathematically and come up to this fatality finally happening 2 times in 100 years or 100,000 years, 10 to the power 4 years. So as ignition has a probability, all these, we call these protection layers, they also have a probability to fail. I think this we can skip, but yeah, a few important things. So we have some flammable liquid spilled over. Probability of this liquid catching fire depends on what's the temperature, some properties, flash points, etc. So, for example, if you petrol, probability of catching fire is 3 times more than the very high vapor pressure, very low vapor pressure of gasoline flash point. So total acceptable risk, we were saying the safest way to do something is to do nothing. So the acceptable risk would be zero. It's possible to know that. The safeguard risk we can reduce. We cannot make it zero. We can reduce it. We just have to see what is our acceptable risk. What's the level of risk we can say, okay, this is we can accept. Severity level of the risk is the probability of unwanted event to occur. Now, severity, acceptable risk, severity level, you could see 1, 2, 3, 4, 5, 6, 7, 8. So, the Bhopal gas disaster, Chernobyl, they all fall in this category, right? And that's the company's policy. They say, this is acceptable for me, or this is acceptable for me, or this is acceptable for me. So ideally, everybody should target this, low impact, no long-term fatalities. So we have a system here, safety instrumentation system or function, which was pressure, shutting down the plant or closing this wall. Pressure control, pressure safety system, they both are in combination. So final consequence is fire resulting in more than 100 fatalities. So let's say we can have more than 100 fatalities. If this loss of containment can result in fire, we can have 100 deaths, right? Because this plant is located in a nearby area, whatever, for whatever reason. And we say from this table, we are more than 100 people dying. So our acceptable risk is somewhere here, this class. That means this happening, the fatalities happening, our acceptable level would be 1 in 10 to the power 6 years. And yeah, so probably this you remember from your high school. Probability of A happening and B happening, and A and B together happening is PA times PB, right? Even simpler form, if you spin a coin, it lands up in tail, probability is 1 in 2, right? And if you spill 2 coins and they're both landing in tail, probability is 1 in 4. So PA times PB, that's your combination. And we call all these layers independent protection layers. So there is a probability of 1, there is a probability of 2nd, 3rd, 4th, and probability of all of them failing will be probability of IPL 1, 2, 3 all multiplied together. So I have to install so many protection layers that if I multiply their probability, the result should be less than 1 times 10 to the power 6, minus 6. Right? That's the idea. But you cannot keep on adding layers and layers, independent layers. That's also a cost associated with this. Right? So another way would be, if you cannot keep adding more layers, if you cannot add more layers, at least you can make your layers strong, effective. Right? And that is called the SIL, safety integrity level of these layers. Right? So we say we have pressure safety wall. Now we say we have PIC loop. The FIC, the feed control and the pressure control are also connected. We have PIC with the cooling duty. What we said, we sense the pressure here. If pressure is increasing, we reduce the feed flow, thereby reducing the energy inlet. If pressure is increasing, we increase the cooling duty. Right? But what we did, we used the same pressure sensor, right? So one protection layer is this control loop pressure controlling the feed. One independent, or let's say layer is pressure, this pressure controller controlling or varying the cooling duty, right? But they both are not independent because they are using the same pressure sensor. And when we say one protection layer can fail, so pressure sensor, there is a let's say instrument which is sensing pressure inside. It converts this pressure reading into electrical signals. This goes to a computer which has this algorithm. Okay, pressure is now increasing. It calculates what should be the final action on the control board. It calculates how much I have to close the control board. So the signal goes electrically again to this wall. So there is a sensor, there is a controller, and there is a final element. Anything can fail, and that's why this protection layer can fail, right? And since this protection layer and this protection layer is using the same sensor, they cannot be considered as independent protection layer. You cannot say we have two protection layers. It's just one. In order to make these two protection layers independent, what we need to do, we need to install a separate pressure sensor layer, which dedicatedly goes to this loop, and the another one goes to this loop. With this, you separated them completely, right? And now they are independent. So that's what we say. What we were saying earlier, that you need this pressure sensor to do its job when it is required, but it can fail. So it's actually probability of this sensor working on demand. And demand is not 24 hours a day, 7 days a week. Comes sometime because pressure is increasing only once in a while. So these are typically some examples of walls failing, loss of power, those kind of things. So you need to know probability of failure of these independent layers, and you multiply all of this and you come up with your risk, final risk. So for example, probability of pressure transmitter function malfunction or not working when required is 1 in 10. Right. So if I combine for this example all our layers, PIC, PSP not working is 1 in 100 years. So combined probability of failure and demand is 1 in 1000 years, that is 10 to the power minus 3. Right. My acceptable risk was 1 in 10 to the power 6 years. Right. And our current risk is 1 in 10 to the power 3 years. So we still need to reduce the risk by factor 10 to the power 3. Right, for example. So we consider PIZ loop also, then it becomes 10 to the power 4. So final risk reduction required is 10 to the power 2. Right. Then we had a pressure safety valve. So that's also an independent layer. Now we have one safety valve, and we can say it can fail 1 in every 100 years, right? But if I install 2, then combined probability will be 1 in 10,000 years. Because all I need is controlled release of my vapor or liquid, whatever, right? So if I install one, it can fail 1 in 100 years, but if I have two, it can happen. You can argue that when you need it, both can fail. So 1 in 100 years happens coincidentally at the same time. So two can fail in 100 years. So finally, the risk reduction required is factor 10 after considering this PSV also. And this is what you define your safety level of this PIZ group. That it should not fail in 1 in 10 years, it should be failing 1 in 100 years. And how you can increase, so that's how we define anything between 10 to the power minus 1 and 2 is safety 1, level 2, level 3. Level 3 means it has to be absolutely safe, that its probability of failure is 1 in every 1,000 years. And how you can increase, let's say, or reduce the probability of PFT, probability of failure in demand, at the cell level, as you were saying, brakes can fail, but if I do regular maintenance, what I'm actually doing, I'm reducing probability of brakes failing, this happening. The same way, regular maintenance, you install more sensors, more shut-off walls, so more capex and more safety.